Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on the confidence interval on the mean. For this video on this PowerPoint, we are working with x being normally distributed and sigma being known, and an approximation for large sample sizes n greater than 30. And I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos. This is part 3 of the series, and we're picking up in the middle of this example, and you will need to have watched part 2 of the series for this video to make sense. So we're talking about our parts, and we've kind of discussed the upper and lower limits. So we have the distribution of the mean length of parts, and we know that the population mean is probably not over here on the right, over here. Why? Because if it's over there, then the x bar is in the lower tail. If it's any further over there, the x bar becomes into the shaded region where it's unusual. And we know that the population mean is probably not over here on the left. Why? Because if it gets over there too far, it becomes in the other tail, where again it would be unusual, and that gives us the lowercase limit. Excuse me, not lowercase, lower confidence limit. And because for higher or lower means that the mu would be unusual to get a sample mean of the x bar of 163.1. So we have the distribution of the mean lengths of parts, and we have x bar minus an error or an e and a lowercase limit, and x bar plus e for our upper confidence limit. And the population mean is probably not over here and probably not over there. And we have that mean then can be floating somewhere in between those two values. So we now have a range of values that mu can fall between. Notice that it changes directions when the tail hits the mean of 163.1. So we have our formulas for the confidence intervals on the mean. We have two assumptions as we start this. One is that our x is normally distributed and that the population standard deviation, or sigma, is known. So we have x bar, and we have a distance from x bar known as the e, or error, and that error is added and subtracted for that distance from x bar to give us our range. And that gives us our lower confidence limit and our upper confidence limit. And our formula to find the error is z alpha sub 2 times sigma divided by the square root of n, the standard deviation divided by the square root of n. And as we work this problem, that formula will begin to make better and better sense. So x bar minus e and x bar plus e will be our lower confidence limit and our upper confidence limit. So let's go back to our problem with our numbers, and let's construct a 95% confidence interval for the mean. So we have our formulas and we have our numbers. X bar is equal to 163.1. That is our sample mean. Our population standard deviation, or sigma, is equal to 44.6, and our sample size is 40. To find the error, that will equal z alpha sub 2 times the standard deviation divided by the square root of n. First, let's again go back and think about our z of alpha divided by 2. A 95% confident interval leaves 5% for the two tails. A 95% confidence means that we are willing to be 5% wrong, or that we're willing to risk 5%. We will split that 5% between the two tails. Why two tails? Because a confidence intervals are always two tails. We want to find the lower and upper part of a confidence interval. 5% divided by 2 leaves us 2.5%, or 0.25. Alpha equals 0.05. Alpha divided by 2 gives us 0.025. So the z value we need to look up is z sub 0.025. And we can do that using the table or using our calculator. We will only use the z alpha sub 2 is the only z value that goes into the E formula. Why do we only use the positive value into the formula? Because the formula requires us to add and subtract the E, or the error, thus taking care of the negative value. If we subtract it and add it, if we put the negative in it and do the adding and subtracting, it works out to be the same values, and we do not need to do the repetition of that. So again, how do we find the z sub 0.025 using the table? Draw your picture. That gives us 0.025 in the right tail. The area to the left would be 1 minus 0.025, which is 0.975. The closest value to 0.975 in the table, well, actually that value is in the table and gives us 1.96. So our z of 0.025 is 1.96. To do this in the calculator, you would hit second, distribution, choose inverse norm. Your area to the left would be 0.975, and then enter, and rounding to 2 decimal places, you will get 1.96. Remember to always check with your table. That ensures that you're getting and using the same values that your teacher is. Now, here are our numbers again. X bar equals 163.1, sigma equal 44.6, n equals 40. Here are our formulas, and we know that our z alpha divided by 2 equals z sub 0.025 is equal to 1.96. What is that z value? This tells us that z value tells us that the unusual, or our risk area, starts 1.96 standard deviations from the mean. In other words, remember, a z-score is simply the number of standard deviations, and the number of standard deviations until we get 2.5% left in the tail is 1.96. So we have 1.96, that's what this number here tells us, standard deviations. If our standard deviations, if the size of our standard deviations was 2, we could take 1.96 and multiply by 2, and that would tell us the numbers of centimeters we would have. If our standard deviation was 10, we would take 1.96 and multiply by 10, and that would tell us the number of centimeters we have. Well, our standard deviation is 44.6, but this is a central limit theorem type problem where we have a sample mean and we're looking at the standard deviation from a set of means. So we need to take that standard deviation and divide by the square root of 40. So that's where we get the 44.6 divided by the sample size, which is a square root of 40. That gives us the size of our standard deviation. Then we multiply 1.96 times the size of our standard deviation, and that will tell us how far out in centimeters we need to go. We need to go out 1.96 standard deviations times the size of our standard deviation to tell us to go out 13.8217. Notice we really don't want to round that number too much. We want to round in our last step. That is how far out, or the distance between the mean, or excuse me, our sample mean and the tail is. Then we take and add and subtract that distance to find our upper and lower confidence limits. X bar plus the error and X bar minus the error. So that would be 163.1 plus 13.8217 and 163.1 minus 13.8217. And that gives us 163.1 plus 13.8217 gives us 176.9217, and Ms. Borlaug rounds that to one decimal place of 176.9. 163.1 minus 13.8217 gives us 149.2783, or 149.3. At this point, I will pause to say that you really do need to pay attention to what your teacher says about rounding. We have a lot of different teachers and they all have a slightly different philosophy on rounding, so please follow your teacher's rounding rules. Then Ms. Borlaug wants you to fill in your sentence, which says, I can say with 95% confidence that the mean length of parts is between, and then you have your two blanks, centimeters. So in our case, we can say with 95% confidence that the mean length of parts is between 149.3 and 176.9 centimeters. A graphical display of the confidence interval would look something like this. We have a number line along the bottom. Notice that Ms. Borlaug chose to count by tens. She roughly estimated the 149.3, the 176.9, and the sample mean of 163.1, and labeled it the 95% confidence interval on the mean length. And this is a good way to display your results in a meeting so that everybody can understand that you're pretty sure that all your population mean falls somewhere in between those two values. Let's do a brief review of the previous example, and this is the way that you would work the problem from the start without all the added little bits that we did as an explanation. We have the example. A company manufactures parts. A random sample of 40 parts is taken and the lengths are measured in centimeters. The sample has a mean length of 163.1. Assume the lengths are normally distributed with a standard deviation sigma equaling to 44.6. Construct a 95% confidence interval on the mean. First of all, you pick out your important numbers. X bar equals 163.1, sigma equals 44.6, and n equals 40. Here are your formulas. I will not read those, but the first thing we want to plug in is our z. Our alpha is 0.05. Divide that by 2, we get 0.025. Look up the z-score that goes with 0.025, and that gives us 1.96. Take 1.96 times the sigma, which is 44.6, divided by the square root of 40. That gives us 13.8217. Take the sample mean, which is 163.1, plus 13.8217, and 163.1 minus 13.8217, and that gives us our, well, she put those in the wrong places, but that does give us our upper and lower confidence intervals. And then you write your sentence. For Miss Borlaug, the sentence is important. You need to verify with your teacher how your teacher, he or she, wants you to write the answer. I can say with 95% confidence that the mean length of parts is between 149.3 and 176.9 centimeters. As you write your sentence, I do need to pause here because I did not say it before. The sentence will remain the same with certain things changing with each problem. The 95% will change every time you do the problem. It may be 95, it may be 99, it may be 90, it could be 80, it could be 98, it could be 96. That changes, so that part will change. The length of parts changes based on what your problem is saying. Your upper and lower confidence interval, of course, the numbers change, and the units change at centimeters. That could also change. I am so sorry this has taken so long. These are very long, but I hope that this is helping you. And we're going to pause here and conclude this video. I hope this video was helpful. We will pick up with a second example in the next video. Thank you for watching.